Hey everyone. In this video, I'm going to provide a brief overview of the key concepts of power analysis, as well as some of its critiques, and present a basic framework that allows us to um, declare research designs and conduct power analysis in a coherent framework. Okay. So the first paper that is assigned for this week is Cohen 1992, a power primer, which is basically like a traditional overview, kind of conventional overview for power analysis, the way it is done in psychology and in social sciences in general. And it's a useful, first introduction because it provides some intuition for some underlying questions. For example, how to think about small or medium or large effect sizes, and what the implications are for the statistical power and for necessary sample sizes for basic for kind of basic types of tests, for example, differences in means or significance of correlation coefficients and so on, right? So what this paper does is it doesn't really go too much into the underlying theory, but provides a very brief introduction and some intuition as to what necessary sample sizes are for basic tests with assumed effect sizes and assumed power. Okay. So the way this is structured in Cohen, or in general the way statistical power analysis is structured, is it basically examines the relationship between four key variables that are involved in any type of statistical inference. Okay, and those four components of any type of analysis are the following. The first one is the sample size, which you usually denote as capital N. And in conventional power analysis, the goal is usually to estimate the necessary sample size that we need in order to be able to detect our effects with sufficient power prior to data collection, right? So usually we would want to, before we start collecting our data, conduct a power analysis, and the goal of the power analysis is to kind of provide an estimate of how many respondents, how large of a sample do we need to collect in order to actually provide reliable estimates for our quantities of interest. Okay. The second component that is part of this relationship is the population effect size, and that's kind of the true effect size that is the goal of our inference, right? That's ultimately what the effect that we're trying to estimate and that we're trying to make an inference about. And specifying this population effect size, we have to make an assumption about what this true effect would be in order to make a judgment as to what the statistical power is to recover this effect given a specific sample size, right? So specifying this population effect size is the most difficult part in any power analysis, because it essentially requires us to either rely on prior studies or previous published research or prior knowledge to kind of assume reasonable effect sizes and then compute power based on those effect size assumptions, right? And so this is really difficult, but one thing that is useful in the Cohen piece is that it kind of provides some intuition and some guidelines regarding conventionally small, medium, or large effect sizes for some of these basic tests, like differences in means and correlation coefficients and so on, right? So that provides you some initial intuition, what constitutes a small effect, what constitutes a large effect in the context of a power analysis, right? So for example, like one of the examples in the Cohen paper is that like a medium difference in means, like a medium effect size when you look at difference in means, is for example half a standard deviation, like as a kind of rough guideline, the way we think about effect sizes, right? Of course, this depends a lot on context and on the underlying substantive question of interest, but it at least provides some initial intuition. Okay. The third component of power analysis, or the third component of any exercises in statistical inference, is the significance criterion. Right. So this is the risk of mistakenly rejecting the null hypothesis, and usually the standard cutoff is of course p smaller or equal to 0.05 in a two-sided test. Right. So we usually set the significance criterion at 0.05. And then we have statistical power, which is usually denoted as 1 minus beta, which is the probability of rejecting a false null hypothesis, right? And this, the kind of conventional, like standard sufficient power value is usually 0.8. So usually we want to achieve at least 80% power, which means we have an 80% chance of rejecting the null hypothesis conditional on the null hypothesis being false, okay? So I mentioned in the beginning that usually in conventional power analysis, the goal is usually to basically take an assumed population effect size, ideally from prior studies, prior research, assume a significance criterion that you're going to use in your study, and then assume a level of a power that you want to achieve, like 80%, and then compute, okay, given these specifications, what is the necessary sample size that we need to collect? How much data do we need to collect to kind of achieve that level of statistical power, right? But the key here is that estimating the sample size is not necessarily, it doesn't have to be the goal, right? The key is that any of these four components ultimately can be expressed as a function of the other three, right? So sample size can be the goal, estimating the appropriate sample size can be the goal of a power analysis, but it doesn't have to be, right? You can also work with a fixed sample size and ask the question, okay, how large of a population effect size can I estimate with sufficient power? Or you have a sample size and you have a prior as to what the effect size is, and you want to know, okay, given the setup, what would the statistical power actually be, right? So these four variables that are part of any kind of statistical inference they are interconnected and they are functions of each other. And so as soon as you basically make assumptions about three of those components, you can express the fourth component as a function of those remaining three. So any of those components could be kind of the goal for your power analysis, essentially, right? All right, so that's the basic setup, right? We have a sample size, we have a assumed population effect size, we have a significance criterion, and we have statistical power. And power analysis basically leverages the relationship between these components in order to estimate, for example, required sample sizes, right? But there are problems with this kind of procedure. There are kind of issues with this basic framework, and Gelman and Carlin kind of make in this paper Beyond Power Calculations make the point that these traditional power calculations are ultimately flawed due to a narrow focus on statistical significance, right? So once you're kind of only focused on receiving statistically significant results, then these power analysis can actually be flawed and give you kind of false confidence in your results, right? So especially, and that's one thing that they especially emphasize, is this issue with post hoc like power analysis. So after you conduct a power analysis after you're running your experiment and kind of examine after the fact what the power of your statistical tests were, right? And so the argument here is that conditioning, for example, on statistical significance for small sample studies, these post hoc power analysis can actually be quite problematic, because they basically they exaggerate the confidence that you have in the results that you're finding, right? This is a really important piece to kind of take into account and kind of think, use to kind of think critically about the power analysis framework and the focus on power and statistical significance in of itself. And it also emphasizes one thing that even in the Cohen papers mentioned, but it's not really clearly outlined, how exactly you incorporate external information to derive your assumed effect sizes, right? This is, Cohen mentions that this is the most difficult task, but it doesn't really provide a lot of guidance as to how you can actually integrate other effect sizes or results from previous studies in your analysis, right? And so one of the arguments that Gelman and Carlin make that make it so difficult is that the published effect sizes tend to be overestimates of the true effect size, right? Because we have a publication bias, because only significant results are more likely to be published. That means if you use published effect sizes as kind of guidelines for your power analysis, then ultimately you're assuming effect sizes that tend to be larger than the true effect sizes, because you're basically selecting only on the effect sizes that were being published and not the ones that are out there basically hidden in file drawers, right? So that's one fundamental issue with selecting and incorporating external information from published studies, for example. Right. So ultimately, they provide an alternative framework for design calculations, which can be applied both pre and post data collection. Right. They also look at power as the probability that so they kind of think about it in a slightly different way by emphasizing the role of kind of replicating an experiment and power as a characteristic of the extent to which replicated experiments kind of yield the same result. So they define the power as the probability that the replication, drep is basically the estimate in your experiment for one replication, is larger in absolute value than the critical value that is considered to be or to define statistical significance in this analysis, right? So again, drep is the estimate that would be observed in a hypothetical replication study with a design identical to that used in the original study, right? So we're kind of thinking about this in the context of repeated experiments and, thinking about this, the power as the probability, that's... ask me later. The probability that in a given replication, the critical value is or the estimate is larger than the critical value to ultimately identify statistical significance. Right. This is equivalent to or it's very similar to the way we thought about power in the Cohen piece, in the sense that whenever the drep is beyond the critical value, it is statistically significant, and assuming that the null hypothesis is false, over a lot of repetitions, that is equivalent to this rejection ratio of a false null hypothesis, right? But it points the emphasis on this replicated experiments and the kind of the sampling distribution over repeated experiments, right? So it's a slightly different focus by invoking this idea of the replication effect size. Okay, but this is not the key point. The key point is that we should basically move beyond simple power and basically examine two other statistics related to the design, and one is called the type S error rate, which is the probability that the replicated estimate has the incorrect sign if it is statistically significantly different from zero. Okay, so that's the sign error rate, where conditional on conditional on the estimate being statistically significant, there is still a chance that the estimate that we have has the incorrect sign, right? And the important point here that is that this is not equal to the significance level, right? It's quite possible for a result to be significant, for example, at the 5% level, which means that the 95% confidence interval entirely excludes 0, and there's still to be a high chance that this interval is on the wrong side of 0, right? And this is one of the key points, that this type S error rate is not equal to the significance level, and especially with lower powered studies, with studies with smaller sample sizes, as soon as you condition on statistical significant events or statistically significant coefficients, you can still have a very high type S error rate. You can still have a very high probability that your true effect is actually, has actually the opposite sign, right? And that's a key point here. Next, the third component is the exaggeration ratio, or the expected type M error. And this exaggeration ratio describes the expectation of the absolute value of the estimate divided by the effect size. It's if statistically significantly different from 0, right? So again, conditional on the effect being statistically significant, we basically we can basically specify, after conditioning on the effect being statistically significant, how much it, in expectation, kind of exaggerates the true effect size. So how much it is, in expectation, tends to be larger than the true effect size, right? And again, this is not a trivial ratio. This can actually, depending on the design, can actually be quite large, where, if we kind of condition on statistical significance, we know that the effect size that we see is very likely to be an exaggeration, is very likely to be larger than the true effect size, right? And this is also a problem that has to be taken into account beyond simple statistical power, right? Okay, so the key point, and I have to move myself a little bit here. Oopsie. Is that significant findings from studies that are underpowered are likely to produce wrong answers in terms of direction and magnitude of the true effect, right? So if we have studies that have small sample sizes that are underpowered, we can still find significant effects. And the key thing is that it's a common misconception that if you happen to find statistical significance with low power, that this is actually a good thing, that you have, something, that you actually achieved something, really impressive, because even though your power was so low, you still found something significant, right? And that's the key misconception, because as soon as you have a low-powered study, a study with small sample size, and you kind of condition on the effect being statistically significant, then you have a high type S error rate, and you have a high, in many cases, high exaggeration ratio. So in many cases, you produce the wrong answer in terms of the sign of the effect, and you are very likely to exaggerate the magnitude of the true effect, right? And that's the key point. So the take-home message from this paper is that we need to use larger sample sizes than what is commonly used in psychology, and what, for example, in the Cohen paper is outlined, would in many cases be kind of insufficient according to Gelman and Carlin. Okay. Okay, I think I said everything that I wanted to say about Gelman and Carlin. Let me move on to the third paper that we were assigned to read for this week, which is Blair and co-authors, Declaring and Diagnosing Designs, right? And so this paper provides a framework for formally declaring the analytically relevant features of a research design, which ultimately allows us to conduct power analysis and examine type M error, type S error, and other features of the design prior to data analysis. So it's a great package in R, and it's a great framework that really kind of helps you to, or provides a coherent framework to plan a study, set up the design, think carefully about the underlying assumptions regarding your data generating process, and then kind of explore what the consequences are with regard to statistical power, bias in your estimates, and so on, right? So what are the elements of a research design that we need to kind of declare prior to analysis? There are a couple of components. The first is a causal model, which is denoted as M, which basically describes how the world works. That's the underlying kind of true data generating process, which includes a specification of the variables that are included, their functional relations, as well as the underlying probability distributions for exogenous variables. For endogenous variables, we kind of also specify how these endogenous variables are dependent or influenced by other exogenous factors. Okay, so this is kind of the complete data generating process. Okay, then the second component of a research design is an inquiry, or I, about the distribution of variables. Right, so this is ultimately specifies the quantity that the researcher wants to learn about. Right, this is kind of the underlying question. Do we want to look at the distribution of a difference in means, and or things like that. Any type of inquiry, any types of kind of quantity that you want to learn about, ultimately you could think of as examining the distribution of a variable or combination of variables, and that is kind of defined as the inquiry. Okay. Then we have a data strategy, which is denoted as D, which basically generates data, which we denote as D, on X under model M. Okay, so that basically includes things like sampling strategies, treatment assignment, measurement techniques. So those are all the kind of components that, based on the underlying causal model, kind of create your observed data that you ultimately can use to estimate your model. Okay, and then we have an answer strategy A, which is based on the data and includes the estimator used, for example, an OLS model with interaction terms or things like that, right? So by basically declaring each of these components of a research design, we can basically explore what they call diagnosings. So basically fact or statistics like bias, power, type S error, type M error, and other types of diagnosings using Monte Carlo simulation. So basically the underlying idea is we specify our causal model, we specify kind of what we want to learn about the underlying population. We specify a data strategy involving treatment, measurement, and so on, and we specify our estimator, our answer strategy, how we actually try to kind of find out about the underlying causal model. And then based on that complete declaration, we can then simulate, using Monte Carlo simulation, simulate repeated iterations of that underlying data generating process, apply our answer strategy, and examine to what extent our estimates are biased, to what extent we have sufficient power, and so on, right? So it's a really powerful framework that provides a kind of a coherent setup to go through all the steps of a research project, of a data collection, including the analysis, and makes it really easy to, for example, compute power, and so on. And also makes it easy to explore variations in design when it comes to randomization. Should you use block randomization? Should you use, a 3-arm design versus like a 2x2 design? And these are all important questions where it's sometimes not quite easy to, it's not straightforward intuitively to know which specific design choice is better in a given scenario. And so as soon as you kind of get into those details, it's really useful to kind of think about the research design in this framework, and then explore the consequences of different assignment strategies, analytical strategies, estimators, and so on, based on that framework. All right, so that's it for the overview. In the next video, I'm going to actually show you basically an example of the declared design package. I'm going to go through a quick study design and show you how to set up basically declare design from start to finish and conduct a power analysis.